As I said, this isn't an actual exam question, but it's very similar to the kind of thing that you might get. So this is the standard of thing that you might get asked to do about this particular bit of stuff on capacitors. The first one, to be fair, in the exam, they tend to save time and draw it for you. But remember my rule about exam questions. If this was actually given to you in the exam, I can bet you they wouldn't draw the diagram like that. They would leave some key values off or something like that. So drawing it yourself is probably as good as anything. And it's a useful thing. Any A-level question, make sure you've got a complete diagram, okay? Either because they've asked you to do it, or because you've actually drawn it for yourself, okay? And as always, check their diagram, okay? If they draw a diagram, or they say the circuit is set up as shown in the diagram, then there's a very good chance that they won't put all the information on, all right? You'll see this more when we look at some actual A-level questions. They tend to leave stuff out, okay? Anyway, there's the answer to A. 12 volt battery, 2000 ohm resistor, 50 millifarad capacitor, a switch and an ammeter. They tell you the circuit is completely a series circuit, so it's just a big loop. You can put them anywhere you like. That would be it for a couple of marks, okay? And this is very useful in terms of understanding what's going on, all right? So make sure you've got a good diagram. If they set you this question like I've done with no diagram drawn, you might even want to just draw your own diagram to make sure you've got your ideas straight. Now, if you look at part B on your sheet, question B, that focuses on the instant before it's turned on. So that's exactly how the circuit is. At t equals 0, sort of summarised on the right here, at t equals 0, that's what part B is all about, before the thing is switched on, okay? Before the thing is switched on, they ask you a couple of things, or at the instant where you just shut the switch. So we've shut the switch, and there hasn't been time for an electron to go round. It's a bit of a mad idea, but at the absolute instant that you turn it on, so before any charge moves round, they want you to decide what the voltage on the capacitor might be and what the voltage on the resistor might be. All right. Now, the good news is this is very easy. What's the voltage on the resistor?
12.
Yeah. Therefore, what must be the voltage on the capacitor?
0.
Why is that true? Why does the capacitor have no voltage? Because what hasn't happened yet? Yeah, no charge has moved around the circuit. Why do capacitors build up little voltages on them? It's because charge has moved around. If no charge has been moved around, then there's no voltage produced. All right. Remember, we always talk about capacitors charging up, but remember, as they charge up, they voltage up. It's a strange phrase, but you need to remember it. There's no charge on this capacitor. They may even say that in the question, maybe. There's no charge on the capacitor, and that means there is no voltage. All right. So the voltage on the capacitor is nice and easy. It's got to be 0. All right, because it isn't charged yet, therefore it isn't voltage. Whatever charge does, voltage does. Remember that graph of Q against V? It's an absolutely straight line. Whatever the charge does, the voltage does. So if the question told you the capacitor is not charged yet, they just told you what the voltage is. It must be 0. Okay. Ammeters, as you know, in exam questions are perfect. They have no resistance, so that won't be involved either. The only thing left in the circuit is the resistor, and so the resistor VR is going to get the full 12 volts. All right. The capacitor will have no volts across it. The resistor will have the full 12. Now, a bit more interesting, try not to give away the answer to the first bit. They then say a bit later on, the capacitor has 4 volts across it. As always, it's useful to use the diagram. The capacitor now has 4 volts across it. Obviously, some charge has gone round, some charge has been separated. That means that you'll produce a voltage across your capacitor, and that's obviously managed to build up from 0 to 4. Okay. Things they want you to work out, I'd probably do the other way around actually. Let's first of all do the voltage on the resistor. What's the voltage on the resistor got to be if the voltage on the capacitor is 4? be 8, isn't it? The ammeter doesn't matter. It's a year 10 circuit. Two things in series getting 12 volts. If one gets 4, pretty obviously, the other one gets 8. Simple as that. All right. I know capacitors are nasty, horrible year 13 things that behave in a strange way, but they are fundamentally electrical components. And if that's got 4, it doesn't matter whether it's a capacitor or a cuddly toy or a food mixer. It doesn't make any difference. If it's got 4 volts across it, the other thing in the circuit is going to get 8. All right. So if we do the second part first, VR's got to get 8. All right. Don't be put off by capacitors, although they're very complicated. Basic electricity still applies. Kirchhoff's second law applies to anything. All right. You can put a football, a computer, and a bag in series with a 12-volt battery. What will the 3 voltages add up to? 12 volts. All right. So don't forget your basic electricity. If that's 4, that's got to be 8. Doesn't matter how horrible that thing is. Okay. Now they want to know the charge on the capacitor. Resistors don't retain any charge, so don't ask about that. They want to know the charge on the capacitor. Now, can we remember from last time, from our triangle? Formula for Q? C times V. All right. From the fundamental equation for capacitors, if you were living in a cave yesterday and didn't come to the lesson, you'll still know this is basically the fundamental equation for capacitors. C equals Q over V, giving Q equals C times V. You've got to learn this. This is so easy to get wrong. If I'd written Q equals C over V, how many people would have put their hands up and spotted it straight away? Exactly. Right, put the numbers in. 50 millifarads. Get used to your millis and your micros and your nanos, because that's all the time with capacitors. The voltage across the capacitor at the moment, remember question C is set when the voltage on the capacitor is 4. All right. Now you can, if you want to, can I just share with you a way to make these questions a bit easier? You can, if you want to, put that in your calculator as 50 times 10 to the minus 3 times 4, and off you go. Two things to mention there. One, that's more complicated than you need to be. Secondly, you're introducing an area of possible mistakes. Okay? You can possibly make a mistake there because times 10 to, then using the X button on your calculator and stuff like that, it's quite possible to make a mistake. So don't make this harder than it needs to be. 50 millifarads, you're all thinking that's 50 times 10 to the minus 3, and you're right, but let's just make things a bit easier. Let's just do the 50 times 4. Yeah? That would give me 200. Now 200 isn't yet the right answer. If I want my charge to come out in coulombs, my capacitance needs to be in farads, which it's not, and my voltages need to be in volts, which they are. So if I did very quickly 50 times 4 and said the answer is 200 coulombs, I'm wrong, because I haven't put my capacitance in farads. I put it quite sensibly in millifarads. Well, there's an easy way to get around this, which is to do that. Okay? Don't immediately rush for the calculator and the X button and do things like that. The more buttons you have to press, the more mistakes you can make. This is very easy. 50 millifarads times 4 volts is 200 millicoulombs. All right? And if you think about it, you might just think I fixed the numbers to make that happen. This is going to happen all the time in capacitors. These are always going to be millifarads, microfarads, something like that. The voltage is normally just going to be a single number, all right? So this is something you can do all the time. Those of you who did 50 times 10 to the minus 3 times 4, you will get the right answer. 200 millicoulombs, what's a slicker way of writing that? 0.2. Again, a coulomb is a very large unit of charge. So don't be surprised to always end up with fractions of a coulomb. 1 coulomb is a lot of charge. Okay? So 200 millicoulombs, simplest way to do it. Okay? Gives us 0.2 coulombs. So C part 1 is going to be 200 millicoulombs, which would be fine. A bit more sensibly written as 0.2 coulombs. Everybody happy? No? Yeah. Right, part C. I've written it the way the exam. Sorry, part D. I've written it the way the examiners would write. I finished that one. Sorry. They want the current. Finally, for part 3 of C, they want to know the current. Okay. Any suggestions how we might go about that? Again, don't forget your basic electricity. There's a horrible capacitor in there, but the other components in the circuit will behave in the ordinary way. How might we get the current? That's it, just use Ohm's law. Just look here. Again, don't be looking at this circuit thinking it's a horrible year 13 circuit, it's got capacitors in, how can I possibly do this? Here you've got a nice simple bit. You've got a 2000 ohm resistor and we've calculated 8 volts. So all you need to do is use Ohm's law, I equals V over R. Voltage is 8, be careful. Remember we talked about in year 12, you can use these laws anywhere around the circuit, but make sure the numbers you put in apply to the component. So this resistor is not getting 12, it's not getting 4, it's getting 8. It has a resistance of 2000 ohms. Yeah. And again, don't need to reach for the calculator, particularly if you halve top and bottom, that's 4 over 1000. Yeah. Which is 4,000, isn't it? Isn't that 4 milliamps? Yeah. You can use your calculator if you want to, you get 0.004, it's 4 milliamps. Alright. 8 over 2000 is 1 over, sorry, it's 4 over 1000, which will give you 4 milliamps. Okay? People with calculators, did you get that? Yeah. So this one here is going to be 4 milliamps. As I said, get used to the milli and the micro stuff. It's going to be in every single question. Okay? Everybody happy with part C? Right, let's have a look at part D. Yeah.
In C, it says the current in the circuit, not in the resistor.
Ah, good point. So we've worked out, you're quite correct, we've worked out that as 4 milliamps. So 4,000th of a truck per second comes through the resistor. What current are we flowing into the battery then? What do you know about current in series circuits? It's the same. This is the reason, I think if I was a naughty examiner, I'd perhaps write that in. Calculate the current in the battery, calculate the current in the capacitor, calculate the current through the ammeter, calculate the current through the battery, they're all going to be the same.
So,
Yep.
why is it only 8 volts then instead of the 12 from the battery?
Because the capacitor's got 4 of them.
And you don't count that in the total circuit?
You do. The total voltage in the circuit is 12, 8 of them across the resistor and 4 of them across the capacitor.
But would it being 12 not affect the charge? Because V equals IR, so if you're using 8 volts or 12 volts you get a different result.
You do. You can't use 12 volts here because only 8 of the 12 volts are across the resistor.
Right.
And you can't use 8 or 12 here, you have to use 4 because the 4 volts are across there. So that's a good point. There's 12 volts total in the circuit, 8 volts across here, which is why we used 8 there, and 4 volts appearing here, which is why we use 4 there. It's a good point. Make sure you're sharing out your voltage. Remember series circuits, the voltage shares out, the current stays the same everywhere. All right. So it's a good point there. The current is going to be 4 milliamps all the way around. Okay. In a series circuit, the current is the same everywhere. Let's have a look at D. The capacitor now is fully charged. Again, you might think I'm just moaning because it's just getting the words right. Not really. Whenever they say a capacitor is fully charged, A, they're wrong. It's got the same charge as it had before, but some of it has been moved from one side to the other and is being forcibly kept apart by an insulator. All right. Fully charged is wrong. However, you might think, I don't care about that. What's more important is fully charged isn't going to help you solve the question. So can we absolutely weld those two words together in our heads? The charge level of the capacitor and the voltage level of the capacitor, whatever one does, the other does exactly the same. Remember that QV graph, it was a perfect straight line. If the capacitor is fully charged, that means it's fully voltaged. All right? The capacitor now has as much voltage across it as it can possibly have. Okay? They will always say capacitor is discharged or fully charged. That's A, wrong, and B, not much use. You need to immediately, when they say the capacitor is fully charged, you need to think, right, that means it's fully voltaged. What's the biggest voltage the capacitor could get across it? It's going to be 12, all right? So, if I just lose that bit there, we're now going to have 12 volts across the capacitor. Hopefully that solves the first question, which is to explain why the current drops to 0. Why will the current now drop to 0 for 2 marks?
The voltage across the battery.
Sorry, what about the voltage across the battery?
Do we have any?
There's still 12 volts across the battery. There's 12 volts across the capacitor.
The equilibrium value is 0 volts.
That exactly. The current, the sort of net voltage, think of it, the battery's pushing that way, all right? Capacitor's pushing that way. They push against each other, all right? Capacitor and the battery will push against each other. And if they're both pushing with 12 volts, a nice way to think about this, it's like getting 2 torch batteries. You can try this at home. Get an old torch with 2 1.5 volt batteries. Seen those ones? Take the battery out the back, turn one of the batteries round and put it back in. What will the torch do when you put that inside it? Won't work. How much voltage is the bulb at the end getting? 0. So think of it like 2 torch batteries connected the wrong way around. All what will happen is they'll get warm, the bulb will get nothing, and nothing else will move in the circuit. All right. So if you had this as an exam question, 2 points I think for this one. The voltage on the capacitor has now reached 12. If they say the capacitor is fully charged, what they mean is, more usefully, is it's fully voltage. So you need to say, if this was a 2-mark exam question, first of all, the voltage on the capacitor will reach 12 or whatever the battery voltage is. That means V total, or the net voltage, you with me? The total voltage in the circuit, the net voltage in the circuit is now 0, all right? And that's why the ammeter, if we drew a graph, it would look like that. Current against time will drop down to 0, okay? If you've got this little sketch graph, that point there happens when the voltage on the capacitor equals the voltage on the battery. All right. Once that happens, exam boards say it's fully charged, fairly useless statement. The point is it's fully voltaged. It's now matching the battery voltage, and therefore there's no current flowing. Okay. Everybody, look at that. Last one: energy stored in the capacitor. We know an equation for that, don't we? Energy stored in the capacitor is half CV squared. You can actually do half QV. Because you do know, well, you did know the charge, but it was obviously for a different voltage. Let's be careful here. A half times the capacitance. Well, again, don't immediately start rushing into standard form. Standard form is an area where people make mistakes in exams. So if you can avoid using your calculator and using the standard form button, there's just one less finger pressed to get wrong. The voltage. What voltage do we use now? 8, 4, 12? 12, isn't it? When the capacitor is fully charged, it is fully voltaged. It has the full 12 volts. All right. So, as people have mentioned before, you've got to be clear to use the right voltage. If they'd asked you the energy stored here, you'd be using 4 volts. Okay. Again, there's probably an easy way to do this. I'll try and do it without a calculator. Half times 50 millifarads, 12 squared is 144. All right. Half of 144 is 72. 72 times 50 milli things. 72 times 50 is 7,200 over. It's 3,600, isn't it? 3,600 millijoules. See what's happened to the milli? You look at that and think, yes, let's stuff that in my calculator. It's 50 times 10 to the minus 3. There's a much better way of doing it. Look, half is just a half. 144 is 144. This is the only thing in your calculation that's got milli in front of it. Lower down the school, you were taught to immediately put everything in the right units at the start. That's a good way of doing it, and you can do it that way. You just make it unnecessary. You've only got 1 milli here. So all you have to do is just carry the milli along. I've ignored the milli bit. I've done my 50 and the 144 and the half. I get 3,600. 3,600 millijoules. Those who used a calculator, is that right? What's a better way of writing that? 3.6 joules. All right. So 3.6 joules is the answer there. Okay.